In traditional decentralized finance, routing capital is a manual process. A human operator clicks through interfaces, configures gas settings, and signs individual bridge approvals. On the right, a natural language command instantly generates and executes a cross-chain cryptographic blueprint. That hesitation on the left, the latency between human intent and manual execution, results in direct economic leakage. By the time a human processes market data and clicks approve, optimal liquidity windows have already closed. When the coordination layer is automated, the protocol moves from a static record of ownership to an active execution engine. This allows capital to move at the speed of application programming interfaces, bypassing the delays inherent in manual confirmation. Because execution happens strictly at the machine level, the most powerful financial protocols scaling today lack traditional user interfaces entirely. They operate out of sight. In institutional finance, execution speed determines the capture of value. When systems analyze and decide faster than human biology allows, interface-driven operations become obsolete. This operational shift is managed by the Denarii Orchestrator. It functions as a multi-chain AI coordination operating system, explicitly designed to strip human interaction out of complex treasury execution. Looking at this live system dashboard, the scale of this autonomous architecture is quantifiable. There are currently over 128,000 active agents, concurrently managing more than $2.4 billion in on-chain transaction volume. Bridging raw artificial intelligence activity with strict institutional finance requires highly specialized middleware. This is the Agentic Finance Translation Layer, or AFTL. The AFTL serves as the financial nervous system for enterprise infrastructure. It translates unstructured AI decisions into mathematically verifiable, policy-bound economic actions. To understand how autonomous capital actually moves, we will trace a single enterprise intent from its initial text prompt through the translation layer and directly into final settlement. Without this rigorous translation stack, deploying artificial intelligence with institutional spending authority is an unacceptable financial risk. The AFTL provides the requisite containment. Autonomous systems executing thousands of microtransactions per second quickly hit a bottleneck on single-chain architectures. They require infrastructure that resolves the blockchain trilemma, balancing speed, security, and decentralization simultaneously. To support machine-to-machine micropayments, the Denarii Orchestrator utilizes a unified cross-chain control plane built on 3 specific ledgers, known as the Trinity of DLT. The first pillar is the XRP Ledger. It processes high-speed value transfers and natively integrates the ecosystem's DeFi token. The second is Algorand, which provides strict mathematical transaction finality. By utilizing the ASA token standard, specifically Asset ID 897649551, the system ensures zero fork risk during automated state changes. The final pillar is Hedera Hashgraph. It manages throughput rates exceeding 10,000 transactions per second, while generating the sub-second verifiable audit trails required by enterprise clients. While this multi-chain infrastructure operates seamlessly, access to the orchestration layer is heavily restricted by a strict token gating model. System architects and enterprise users must hold at least 2% of the total native DFI token supply in a verified Web3 wallet to unlock the command dashboard. The result is an environment that eliminates human delay from the workflow, permitting settlement to occur at the inherent speed of the underlying ledgers. The process begins when an enterprise submits a clear mandate. For example, pay the AWS bill using yield-bearing USDC from Aave on Arbitrum. The text is immediately intercepted by LangGraph, which acts as a cognitive splitter. It decomposes the natural language prompt and delegates it to specialized AI models. One node becomes the routing agent. Its sole objective is to compute the lowest cost, most efficient cross-chain path across decentralized exchanges and bridges. Simultaneously, the second node acts as the compliance agent. It verifies the proposed transaction path against strict internal treasury limits and risk parameters. Standard large language models suffer from a structural vulnerability known as the memento man problem. Because their API calls are stateless, agents lose their situational context the moment a session ends. To prevent this cognitive dilution, the orchestrator writes to a persistent, file-based memory architecture structured around the paramethod, projects, areas, resources, and archives. Furthermore, a continuous heartbeat check-in loop forces the agent to read its designated persona and overarching organizational goals from this memory system before executing any new delegation. This entire cognitive process is housed inside temporal, which functions as the system's durable execution universe. If a network bridge halts or an RPC node drops out, temporal does not fail. It simply pauses the workflow state and automatically retries once Wekanshin stabilizes, completely preserving the entire context. By combining Landgraf delegation, para-memory, and temporal's fault tolerance, the system ensures highly rigorous financial reasoning happens long before capital is authorized to move. Importantly, these reasoning agents do not hold raw private keys on local network file systems. This boundary eliminates the risk of third-party supply chain exploits. Once the path is optimized, the unsigned instruction is sent to a secure execution enclave known as the vault. Here, a Coinbase multi-party computation system enforces a 2 of 3 threshold signature. A valid cryptographic signature requires one mathematical approval from the AI agent determining the route, and an independent approval from the enterprise treasury policy engine verifying the intent. Once the threshold is met, the completed signature fires the payload into Hyperlane, a generic message passing protocol. Hyperlane takes the cryptographic instruction and physically executes the cross-chain swap determined by the routing agent earlier in the loop. The liquidity is then finalized and settled across the high-speed pathways of the DLT Trinity, completing the financial action. Routing capital across multiple decentralized ledgers simultaneously mitigates the severe vulnerabilities associated with manipulating single DEX Oracle price feeds. This enclave architecture creates programmable trust. Human involvement is entirely removed from the mechanics of execution, acting exclusively as the final layer of cryptographic approval. An autonomous transaction is functionally useless to an enterprise if it cannot be parsed by legacy accounting systems. Institutional adoption requires complete auditability. The moment the cross-chain settlement clears, data indexers like Subsquid and Apache Flink capture the raw on-chain transaction hash. This unstructured hash is fed into token books, which decodes the decentralized exchange and bridge events, mapping them cleanly into a traditional double-entry journal of debits and credits. From there, the baseline protocol ingests the journal entry and generates a mathematical zero-knowledge proof. This proof verifies that the accounting logic is sound and pushes the synchronized transaction directly into the company's traditional SAP or Oracle database. The zero-knowledge proof guarantees that the autonomous capital expenditure precisely matches the strict integrity requirements of corporate accounting. From the initial text prompt to the final database update, this entire lifecycle executes without a single human interacting with a crypto wallet interface. By wrapping autonomous on-chain execution in the AFTL stack, complex Web3 operations are rendered simply as standard, auditable enterprise data. Expanding from a single transaction to the macro-level enterprise, this orchestration logic scales up to operate the 5 pillars of enterprise automation. As detailed in the system's structural blueprint, specialized nodes like the quant agent and treasury agent actively assume full operational domains, replacing legacy SaaS platforms, security audit firms, and expensive analytics subscriptions. This automation is driven by the measurability gap, this specific economic threshold where the computational cost to execute cognitive tasks drops permanently below the biological cost of human verification. If machine-generated code is processed without human-grade oversight, systemic errors compound, creating a hollow economy where transaction volume hides unverified logic. The paperclip orchestrator manages this risk by using independent QA agents to audit the workflow at every checkpoint. Cryptographically secure accounting via blockchains was step 1. The automated self-executing machine economy is step 2. The high-throughput mathematical finality and sub-second consensus provided by the XRPL, Algorand, and Hedera construct the exact rails needed for this machine coordination to occur safely. The transition to a sovereign machine economy is an active structural reality. When capital is autonomous, the systems that win are the ones built on execution, not speculation.